Hello once again, class, and welcome to another mock lecture. Today we're going to be tackling inverse trig functions and how to do the differentiation of them. And before we do it, we need to review a little bit about inverse trig functions. Now, by the way, real quick, I actually have a whole entire video dedicated towards defining the inverse trig functions and like where they come from and what their domains and ranges are. And if you want to check it out, I'll put a link in the description below. But here's a very quick rundown. One way that you can think about what an inverse function is, at least graphically, is that it's the reflection of the graph that you're looking at over the line y is equal to x. So I have the sine of x curve. If I want to reflect it over the line y is equal to x, though, we get this, which is not a function because it fails the vertical line test. In fact, the y-axis is a good example of it failing the vertical line test. So what you have to do to make it so that sine of x still goes through all of the possible values between -1 and 1 as outputs, right? Because that's what the sine of x is. It's anything that's between -1 and 1 when you give it an angle measure. You can get all of those values between -1 and 1, showcased here, right? We're getting all the values between -1 and 1 if you truncate the domain of sine of x to be -pi/2 and pi/2. And now if you flip that thing over the line y is equal to x, you get this, which does pass the vertical line test. Now, there's a lot of things to keep in mind when you're talking about inverse functions. Specifically, the domain and the range of the original function become the range and the domain, respectively, for the inverse function. So now we can plug in y coordinates of the unit circle, and what we're going to get are the corresponding angle measures that give us those particular y coordinates. But again, only between -pi/2 and pi/2. So we're really only looking at kind of 1/2 of the unit circle, because that's where, we go from -1 to 1 for the y-axis stuff. So here's a better version, right? This is what the sine inverse function looks like, or we can call it arc sine is another name for it. But basically, here's how it's defined. The sine inverse of x is equal to y if and only if x is equal to the sine of y, and the y is bound by -pi/2 to pi/2. So your output is an angle measure, and I think that's probably the most important thing to point out here. I did put this other bullet point. It says, in other words, if x is an element of the set that goes between -1 to 1, then the sine inverse of x is the angle measure between -pi/2 and pi/2, such that the sine of that angle measure is equal to x, right? The sine of the angle measure that becomes the output of our inverse function is x. This is just kind of a reworded definition of what inverses are. But the main thing is arc sine of x, or sine inverse of x, is an angle. And we could do things like evaluate, right? The arc sine of -1/2. What this is asking us is where on the unit circle do we get a y coordinate of -1/2? What angle measure gives us -1/2 as a y coordinate? Because we're talking about sine. So you might think, oh, it's 11pi/6, right? It's quadrant 4, right? That's where we're going to get -1/2 for sine. However, 11pi/6 is not in the domain of the inverse function, right? It's not in -pi/2 to pi/2. So instead, we have to come up with the coterminal angle, -pi/6. That would be the output here, -pi/6, because it's between -pi/2 and pi/2. And that's the only answer, right? That's the only sine inverse of -1/2 that exists. It's just -pi/6. Now, of course, you can also define cosine inverse and tangent inverse, or arc cosine or arc tangent is another way to say those things, by similarly truncating the domains such that when you reflect them over the line y is equal to x, you get something that still passes the vertical line test. Cosine now is going to be bound between 0 and pi. Right, that's how we had to truncate the domain for that one, from 0 to pi. Tangent, kind of similar to sine in the sense that we are again bounding it between -pi/2 and pi/2. What's interesting is that the tangent function, has all these vertical asymptotes in it. I didn't actually draw them in, but they're all like right here. I guess these are only the only two that matter. But when you reflect them over the line y is equal to x, they become horizontal asymptotes. So our range is similarly bound between -pi/2 and pi/2 for arc tangent. Here's their definitions. Cosine inverse of x is equal to y if and only if x is equal to cosine y and y is between 0 and pi. Arc tangent is equal to y if and only if x is equal to the tangent of y, and again y bound between -pi/2 and pi/2. Okay, that's kind of inverse functions, but that's not why we're here, right? We're here so that we can differentiate these things, right? How do you find the derivative of, let's go with arc sine. So I'm going to let y be equal to arc sine of x, the sine inverse of x, so that the sine of y is equal to x. And then you might be wondering, how the heck did you get here? First of all, I just used the definition, but I probably should have explained, their inverses, so they're undoing each other, right? If I have y is equal to the sine inverse of x, and then I run both sides through the sine function, just like this, well, the sine undoes the sine inverse. So you get sine of y is equal to x, right? And that's what this is. Right? That's why I have that. Now, you do have to be careful because we started with defining y to be a sine inverse function. It does have a specified range. Y can only be something between negative pi over 2 and pi over 2. And now look, it's acting as the input for the sine now, because we did this inverse relationship thing. But really, this is by the definition of arc sine. Okay, let's just differentiate this thing, right? We just learned how to do implicit differentiation. Let's do that here. So I'm going to take the derivative with respect to x on both sides of this equation. The right-hand side is super easy. You just get 1 by the power rule. On the left-hand side, you do have to use the chain rule. It's the sine of some function in terms of x. Okay, so chain rule stuff is going to happen. You take the derivative of the outer function, which is sine. That becomes cosine. You plug in what it was in terms of, which in this case is y. And then you multiply by the derivative of whatever the inside function was, which in this case is just y. And the derivative of y is y prime, right? dy dx. So we get this. And by some division, we're going to get dy dx is equal to 1 over the cosine of y. And technically, I guess we're done, right? We found the derivative. But the astute student amongst you may say, oh, now hold on, Mock. That derivative is not really a function of x, right? It's a function of y. I mean, I guess if you wanted to, you could make it a function of x, right? That should say x, right? Because we know y is equal to the sine inverse of x, so we could have it be like that. But that just doesn't look great. And in fact, there's an easier way to write down what the derivative might be, and it requires a little bit of some cool trig stuff, to be honest. The first thing that I would note here is that because y, right, is bound by negative pi over 2 and pi over 2, right? Since it started here, right, the range of this thing's between negative pi over 2 and pi over 2, and now it's an input, right, for the sine function. In fact, actually here it's an input for the cosine function. Any angle measure between negative pi over 2 and pi over 2 is going to make cosine positive, right? We're on the positive side of the x-axis. And as we know, cosine is the x-coordinate on the unit circle. So this is really good. Cosine then is always positive. Now we also know from a Pythagorean identity that cosine squared plus sine squared is equal to 1. And if I solve for cosine, if I'm going to solve this thing for a cosine so that I could replace this, because I don't want cosine y, I want something else, we get that the cosine of y is equal to plus or minus the square root of 1 minus the sine squared of y. But again, since we know cosine is always positive in this interval, we don't need the negative sign, right? The square root in this identity would just be positive. So then I can replace the cosine of y with the square root of 1 minus the sine squared of y, right? Just based on the identity. Now we also know that the sine of y is just x. So if we have a sine squared of y, that would just be x squared, right? So we get 1 over the square root of 1 minus x squared, and that is the derivative of the arc sine function. All right, so let's write that down. Here it is, derivative of arc sine. You can prove the derivative of arc cosine in almost exactly the same way. In fact, literally the only difference is actually right at the beginning. Here's the entire proof with like no justification, but if you want to look through it, you can. The only thing that's different is that when you differentiate cosine, you get a negative right there. But like everything else after that is the same, including the fact that from 0 to pi, y is always positive. So when you use your identity, you again just use the positive root. Really, I guess it's happening right there. So the proof is like almost identical. but there it is. Tangent is a little bit different. In fact, the proof is more straightforward, in my opinion, than sine inverse and cosine inverse. The derivative of arctangent is 1 over 1 plus x squared, and the nice thing is there is no restricted domain, right? That's the function that looks like this. That's bound in a vertical sense from negative pi over 2 to pi over 2, but you can plug whatever you want, into it. It doesn't have to be between negative 1 and 1 like arc cosine and arc sine. But the proof of this one's pretty cool. You start off much the same way. Y is equal to arctangent of x. So you have tangent of y is equal to x. You differentiate both sides, right? Tan y becomes secant squared y times dy dx. The derivative of x is just 1. You divide both sides by the secant squared of y, and then you just straight up use a trig identity, a Pythagorean identity, in fact. Secant squared y is just 1 plus the tangent squared of y. But the tangent of y is x, so you just replace it with x squared. Right? No unit circle trickery for that one. Just straight up Pythagorean identity, which is pretty cool. There do exist derivative functions for arc cosecant, arc secant, and arc cotangent. I'm not really going to focus on them on this video, but here you go. Here's the screen that people might be looking for in this video. What are the derivatives of all the inverse trig functions? Here they all are. Let's do some examples. All right, example number 1, pretty straightforward. Let's let y equal cosine inverse of e to the x plus x squared. Just differentiate this thing. It's a chain rule, right? You're gonna have to use the chain rule on this thing. When you're using the chain rule, you take the derivative of the outer function first, which is cosine inverse. So we get negative 1 over the square root of 1 minus whatever it was in terms of, which is e to the x plus x squared, and then that thing is squared. And then you multiply by the derivative of the inner function, which is e to the x plus x squared. That's a power rule application. I just distributed the negative in the numerator, and we're done. I wouldn't simplify this any more than this right here. Example 2, find the equation of the line tangent to the curve y is equal to tangent inverse of the sine of x at the point pi over 2, pi over 4. All right, so this one's a little bit more involved. We got to find a tangent line, right? We got to find the line that's tangent to the curve. So first we need to differentiate. Again, chain rule situation happening here. The outer function is tangent inverse, so that derivative is 1 over 1 plus whatever the inside is squared. The inside in this case being the sine of x. Then by nature of the chain rule, you have to multiply by the derivative of the inside, which is the derivative of sine of x. That's just the cosine of x. So okay, we've got our derivative, cosine x over 1 plus sine squared of x. Now we need to find the slope at this point. So let's plug in pi over 2 to this thing. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. I went ahead and drew a little unit circle up here. That's how I filled this stuff in. But you get 0 over 2, which is just 0. So our slope is 0, which means that when you go to plug in this thing for x and this thing for y, this goes away and you just get pi over 4 is equal to b. I mean, the slope is 0, right? So it's got to be some kind of maximum or minimum. And it turns out that in this case, y is equal to just the horizontal line, y is equal to pi over 4 is the line that's tangent inverse of sine of x at pi over 2, pi over 4. Last example, differentiate the sine inverse of xy equal to x squared y squared. All right, here we go. This one's interesting. This is implicit differentiation that we're going to have to do here. I invite you to pause the video and try this. Like, if you've been watching the videos, you know how to do implicit differentiation. You know now that the derivative of sine inverse of something is 1 over the square root of 1 minus that something squared. So give this a try. Also, you're going to need the product rule. But let's go through it. Okay, so first we're going to take the derivative with respect to x on both sides. We do need to use chain rule here. Right, is what's happening. The inside is xy, so this is just normal chain rule stuff. You got 1 over the square root of 1 minus xy squared times the derivative of the inside function, which was xy. The right side is product rule. So that's what this is. This is product rule. Derivative of first function times second function plus derivative of second function times first function. That's product rule stuff. Okay, so now let's actually take the derivatives. Here, this is a product rule situation because it's x times some other function in terms of x. In this case, we're calling it y. That's just normal, implicitly defined stuff. So you get the derivative of the first, which is 1, times the derivative of the second, that's y, plus the derivative of the second, that's y prime, times the first function, which is just x. And I just moved that into the numerator position here. On the right-hand side, this is power rule stuff, and then you have to use chain rule, right, when you're differentiating with respect to x, something that looks like y squared. So it'd be 2 times whatever the inner is, which is y, times the derivative of the inner, which would be y prime, and then times the x squared there still at the end. Now our goal is to find the derivative. We need to get the y primes together. So at this point, we've taken the derivative. The differentiation is done. We just now need to get y prime by itself. So a bunch of algebra is about to take place here. First, I'm going to get rid of the denominator on the left by multiplying both sides by the square root of 1 minus quantity xy squared, which I've now chosen to write as x squared y squared. So it cancels on the left, so we get this thing. My goal now is to get the things that have the y prime in it on the same side of the equation, and the things without the y prime in it on the other side of the equation. So I moved this over to here, and this over to here. Okay, so I got x, y prime. Well, I got this. You guys can just look at that there. Because both of the things on the left have a y prime in it, I factored it out. So the y prime, right, just factoring it out. Really, I should do it like this, but that's where I put it. What's left over is x minus 2y x squared square root 1 minus x squared y squared. I didn't do anything on the right, but I now will, because to get y prime by itself, I need to divide by, all this thing, basically, so that it cancels, and then whatever you do to one side, you got to do to the other side. So I got this, which looks not great. I mean, this is the derivative. You could stop here and say, here you go, right, here's the derivative. You could use it to find a tangent line if you wanted to. That is really annoying if you're going to plug in a point to find what the slope is at a specific point. So you should always look to simplify, and in this case, it simplifies so nicely. If you factor out a y in the numerator, because they both have a y, you get this, 2xy square root 1 minus x squared y squared minus 1. And if you factor out a negative x in the denominator, you get exactly the same thing. It's just written in a different order, but so you could flip that if you wanted to. Those cancel, and you just get that the derivative of this thing is given to be negative y over x. So if you want to find the slope at a specific point where you're given an x and y coordinate, you just divide the y by the x, make it opposite, and that's your slope. So really, this video mostly was just finding the derivatives. It was really showcasing, hey, here's what the derivatives of inverse trig functions are. But as far as application goes, it's just the same stuff we've been doing, right? We can find derivatives, we can find tangent lines. Now we can find them with different types of functions, which is pretty cool. All right, if you want a refresher on inverse trig stuff, make sure you check out the video that I have linked in my description. I hope you guys learned something. If you have any questions, please shoot me an email or leave me a comment below. Thanks a ton for watching, and I'll see you in the next one.